Yeah, so this is work done together with a diploma student, Felix Bertran, and from a competitor university in Munich actually, and Dennis Dietrich, who the particle physicist that you might know. He's one of the guys who keeps walking Technicolor alive. Well, I think he does a good job anyhow. So let me give the motivation. The first slide will be a physical motivation, and then I will turn to a more formal motivation. And the first slide, let me apologize to my friends from astronomy, because it will be very rough there, and I will give you a good reason for why. So the good reason is that these days everybody is speaking about budgets, and of course economical budgets, and most of this talk is about dark budgets, which in economy are considered as being bad budgets. So here's a budget that really matters. The numbers are very rough, and I had to give this in front of a group of economists, and they wanted to hear what's new in physics. And I thought, let me condense what we know about the universe in a chart, in a language that they would be able to understand. So this is the energy budget of the universe. And then I wanted to start with this little nice cake, which is entitled standard model, and then say, oh, no. Forget about that crap. Let's talk about the big five. This follows, look, I mean, this crap contains the standard model of particle physics, and that's an achievement, right? So, and that's actually why science started out, because early on we observed stars, started to wonder what's going on, and this gave rise eventually to astronomy and exact science like physics and mathematics. So, but nevertheless, the message today is this is roughly just about 5% of the total energy budget of the universe. And remarkably, you already need 4 times more to bring these 5% in shape in gravitational bound states that we do observe nowadays, and to keep them in shape. So this is how the universe would look like if you would see the stuff that is keeping it in shape, the dark matter, which you don't see. It's a supporting structure, like when you build a house, you don't want to see the supporting structure. Although I think personally it would have been nice if nature would have done us the favor to let us see this, because it's a nice structure, this cosmic web. So this is from a simulation a colleague of mine from the Max Planck Institute, Simon White, and Volker Springer, which is called the Millennium simulation. So it's called dark. Dark is a bad word from the particle physicist side, because dark means we only have indirect evidence for it, and indirect is a synonym for it's only gravitational evidence. From our point of view, that's not bad. We accept gravity as a legitimate messenger of telling us there is something out that we need to consider. But particle physicists are not so happy, that's why we call it still dark, to honor them. But I think what one has to recognize is that from WMAP and other experiments we have, if we combine them, we have 12 sigma evidence for the existence of dark matter, based on the assumption that Einstein did the right thing. Okay? 12 sigma evidence. Okay? And also it's fair to say that for this candidate we have pretty good, or for this particle we have pretty good candidates in theory, and those who are not motivated by dark matter at all, those were all motivated by technical naturalist challenges the standard model or its necessary embeddings have to face. That's very important, and all of those we have thought about whenever we address technical naturalness. We basically, so far, automatically came as a dark matter candidate. So you need 4 times more, and then you need 4 times more in form of an energy that is called dark energy with a kind of weird equation of state, P equals minus E, and this amount you need to explain the dynamical stage of the universe. It's basically the fuel of the space-time fabric. And if you think that our universe is not embedded in something, it's really fuel of the space-time fabric in the sense that it explains how space-time is generated in an accelerated way. but it's a strange fuel because it never refuses while doing so. So this is basically the short method. It's again called dark. It's again called dark because we only have indirect evidence using gravity to probe that. And if we think about a candidate, there are not much candidates out there that are reasonable. One natural candidate, actually, which comes with the right equation of state, is vacuum energy density, okay? And that shows how important gravity is, because from particle physics point of view, the vacuum energy density to evaluate its total amount is impossible in quantum field theory. Well, it's impossible to measure it in particle physics, I should say. That's a better formulation. So we really need to employ gravity. And here you see a supernova random. That's the way how we do that, among other ways, actually. And that's actually the most important supernova explosion we have witnessed in history. If somebody asks, I can explain why. But otherwise I have no time. So let's talk about the framework we want to use to explore this dark side. And the framework, and that's why I am here, so I have to thank, actually I forgot, I have to thank Sabine for inviting me for having this nice workshop. But I have to thank in particular her because my point of view will be extremely orthogonal to what you guys have discussed before, in that I will only use the UV regime of theories that I will discuss to come up with a quality management for infrared physics. So I will test, or will try to ask, how rigid is Einstein far the infrared? Okay? And I will use the UE to come up with a quality management. And the framework I will use is effective field theory. And this is given here, so just to bring us on the same page in terms of language. So this is kind of the most general effective Lagrangians you can write down in field theory. M could be the mass of a heavy field or the cutoff of your theory. C is some dimensionless number. O is an operator consisting only of fields that have masses much below this big M, so light fields, that's what L is. It's a composite object, and it's divided by this scale M to the power of its mass dimension. Okay? So this is all, I mean, this is basically the shortest way to present what physics is about. So far, physics that we can test in experiments. Now then, physics boils down to the study of only two sets of operators. So one set of operators are characterized by a mass dimension that is larger than 4, strictly larger than 4. And those basically, so E is the energy that is characteristic for this operator. Those processes are generically suppressed by the heavy scale. Okay, and that's good because those operators give rise to unrenormalizable interactions, but the way nature organizes those processes is by suppressing them by the heavy scale. And then there are the other operators that have mass dimension 4 or smaller, and remarkably, those are renormalizable operators, and also they are really relevant operators. They have the highest sensitivity to this cutoff you have introduced here. So in other words, those are the operators that look most promising if you want to go to physics beyond the standard model, for instance, in order to explain the dark contingents and the energy budget I show you on the first slide. Okay? Okay. Let us just check some of these operators and discuss their cosmological frontiers. So let's start with dimension 4. This is not kind of the most sexiest operator, so it's, if you think about QCD, it's just FF dual, and that gives rise to a problem that has the name the strong CP challenge. And a solution of that problem is to enhance the spectrum of QCD by adding one new particle, an axion, that takes care of the small value we need in front of that operator in order to be consistent with observations. I mean, we don't observe strong CP violations. And remarkably enough, this is already a candidate for dark matter. It's not a nice candidate, I have to say. So, but it's a candidate, okay? Fair enough. I hate it, but it's a candidate.
Why is it not nice?
Because, so this guy generically is so light, okay, is so light that it was never in thermal equilibrium with a heat bath in the universe. Meaning, if you want to calculate the structures that this guy would form, you can never expand around the equilibrium state. So, and that's a bad thing in non-equilibrium physics. If you don't have a reliable state around which you can expand non-equilibrium physics, that means you have to solve the full equation. And the full equation then refers to really solving Boltzmann equations, the entire hierarchy of Boltzmann equations. So that's why I would say if nature is so cruel to us, we are a little bit screwed, because that's something we can only solve numerically.
Do axioms interact with them? Is there a certain interaction terminals?
Pardon?
The axioms, do that certain interaction?
Yes. But that doesn't, that's no problem, right?
No,
that's no problem. They have certain.
There are some idea that regarding possible role in dark matter of a light particle which is certain.
No, I think it's definitely a viable candidate. I'm not debating that. I'm just saying it would be very, very difficult to make cosmological predictions with that candidate. I mean, in terms of, can I understand from, say, the first millisecond on, how the structures in the universe evolves to those structures we observe today? With cold dark matter, we can do that. With axions, not. But it's a viable candidate. So then there is a dimension 2 operator, of course, that gives rise to the famous hierarchy challenge. This has a solution, as we heard yesterday, has a solution that is supersymmetry, and supersymmetric embeddings of the standard model quite naturally come with the lightest supersymmetric particle that is stable and serves as an extremely good dark matter candidate. It's also a nice dark matter candidate in the sense that we can predict structures using this, because this guy was in local thermal equilibrium up to the first millisecond in the universe, and that allows us to predict the structures that arises from those guys. Now, remarkable, the operator that is most relevant in the infrared is also the operator that is most sensitive to the UV completion of the theory, has quartic sensitivity to the cutoff of the theory, and this is the operator I can always add to Lagrangian or Hamiltonian, just a constant energy density, space-time constant energy density. And so you see we have increasing UV sensitivity, and as I already told you, that is what the apple here should remind me about, is that the only way we seem to be able to learn about the balance of this operator, or about the challenges this operator poses to us, is by employing gravity. And that's what we want to do. Now let me make that quick, because we already had it in the conference. So if I would like to estimate the contribution of a single massive standard model field, it's an estimate, it's not a calculation, to the vacuum energy density, then generically, after renormalization, what I get is a contribution, that's the most harmful contribution in the sense I will explain, that's proportional to the mass of the particle to the power of 4, and then we have this logarithmic reminiscence of the fact that we had a cutoff to impose here, and that's why we now have a pivot scale nu, our renormalization scale. Okay? Now, just to be careful, that's what Marcus Berger is always stressing in these talks, we always draw just the bubble, but it does not try to pretend that we live in Minkowski space or that we have gravity excluded. The point is, of course, all kind of gravitons would couple to this bubble, okay? But the leading divergent of this diagram is the same than just considering the bubble. But there is no way to trivially renormalize it away, because there is a messenger that can tell us about this bubble, so we are not allowed to just simply set that to 0 by some ordering prescriptions. Now, what is the challenge? There are two ways to formulate the challenge I want to discuss then within massive gravity. One way is to say, look, if I have a massless field, okay, or if I have a massive field as well, let me go to the cutoff. Now, what is the cutoff? Unless we know there is something in the gauge desert between the electroweak scale, okay, and the Planck scale, as long as we don't know there is anything, there's really desert, so let's go to the Planck scale, and that's the way Steven Weinberg formulated in his paper, and you find that the energy density given by this cutoff as compared to the observed energy density is, well, 120 orders off, okay? That's a little bit overstressing the problem, and Weinberg was, of course, totally aware of that. That's just to make a dramatic statement. You can make it less dramatic. Why is it not so dramatic? Look, from my point of view, I think this is an honest effective field theory point of view. Here I have hope, because if the problem with the vacuum energy density would only come with a Planck scale, then we know at the Planck scale new physics should kick in and would be operative at that scale and potentially, or should be able to address that. Okay? Now the real challenge from my point of view is, even if we have solved that, is to consider this contribution here, which is given by a measured infrared parameter of the standard model. So the electron's mass to the power of 4. Okay? So if you calculate the contribution of a single, of just electrons to the vacuum energy density, you are 32 orders of magnitude off. Now there is a very important principle in nature, right? I mean, here I can do this without using quantum gravity to describe that at basically all resolution. We are interested in that. And that's called decoupling. So whatever solves the problem here above is very difficult to imagine and even more difficult to write down to address this issue without spoiling the high precision successes the standard model had since Lab 2 experiments. Okay? I'm not saying it's impossible that in a vacuum there is an IRUV conspiracy going on. It's just difficult to write down models that do that.
Excuse me. Are you, for example, ruling out these models based on commutative geometry where you find the IRUV mixing without even...
No, I'm not ruling out anything. That's just kind of the logic of whatever I want to discuss today. Those models, from my point of view, have other problems. Like, for instance, the great universality of coupling of gravity to matter, and in particular to the Higgs. And I don't understand what is special about the Higgs when it comes to gravity.
I was just mentioning it as a counterexample to the fact that it's hard to do it. I mean,
I see.
It's very easy to do it. Then the rest
Accept it.
gets screwed up.
Accept it.
It's very easy to do it.
Accept it. Accept it. Accept it. You're right. So, my usual comics and my Swedish friends know it already. I have to apologize. I didn't put that on my laptop. I have to say that because in Sweden I can go to prison if I show that. Now, what you can read here is a little guy called Kelvin, and is one of the most clever physicists alive. So what he dreams about is precisely what the non-commutative guys do with the Higgs field. He dreams of basically anti-gravitating, and the point is he wants to be the only guy who can do that. So the rest of the stuff gravitates in the usual way, but he just anti-gravitates. So that's kind of a cool idea. But then he goes to school, and then teachers start to spoil him very severely. So they tell him, look, if you let something fall, everything falls to the center of the Earth. So he does a little experiment and says, no, that's backward what my school teacher told me. The balloon is flying. So his conclusion is gravity is arbitrary. So whenever we want to address these types of problems, that's very important, right? That's why I was yesterday objecting so much about giving up gauge symmetries at the Planck scale, because I also think they are sacred, is that we have to be very careful that we don't lose grounds here. So what we actually want is the following. If we think about the cosmological constant, we want to decrease its impact on geometry. So here we follow little Kelvin, but without, allowing for everything. Still having some rules of the games, and rules we trust in, because they have proven to be very reliable. Now, all I will talk about, and that's why I changed the title, has a nonlinear completion. I sometimes will do linearization just for exhibition reasons, basically. That's very important. I will not work with models of which we know have no nonlinear completion. So if I talk about a graviton, it's only to illustrate what's going on. That's very important. Okay, so, and here's actually what I would consider a good example of breaking universality, which I call here breaking democracy. Okay, then let's check, or let's understand how rigid Einstein is in the IR. And here we go. There is a very nice no-go theorem that was formulated by Marc Henault and Timo Damour in France, which is really remarkable, because if you go through the proof, it relies on very heavy geometrical understanding of BRST and cohomology and so on and so forth. And the question they asked was the following. First, they made an observation. They look, if you consider standard model interactions, most of them involve actually multiples of spin 1 fields, and they are under spell of Young-Mills. That is to say that they have self-interactions. Okay? Now, his observation, or their observation actually, or their question was, is it possible to generalize gravity to such a theory? Okay? Is it possible to introduce, in whatever way I want to think about, multi-gravitons that would interact to each other? And of course, I have to think about which of the gravitons eventually is responsible for geometry. That wasn't me. So, so the theorem actually is a no-go theorem precisely because it says, no, this is not possible. There is no Young-Mills theory of gravity in that sense. And that's a very powerful statement because that can entirely be derived from the proof structure of the theory. Now, that's of course a bit frustrating because we want to think about consistent stress on modifications of gravity in the IR. So what we want to do is to open up new degrees of freedom in the IR. Okay? Then what the theorem basically tells us is not possible. But one of the authors eventually got convinced that one of the assumptions, at least one of the assumptions in this model was a little bit too strict. And the assumption that was too strict was that Mark Hainaut, as usual, is a very strict guy, didn't want to allow for new degrees of freedom. But that's precisely what we are looking for. Okay? It's very difficult to introduce multi-diffeomorphic theories without opening up new degrees of freedom. There's nothing wrong with doing that unless those degrees of freedom have the potential to harm you. So what Damour and also Akani Hamed realized in the same year was we can take Mark Hainaut's proposal and relax his condition. So instead of imposing a multi-diff invariant theory, so M1 and M2 are manifolds, can have different dimensions. And so what they say, let's have as a gauge group just a diagonal of this group. Okay? So this is really a tremendous reduction of symmetries, I agree, but that's okay from our point of view. Now then it became possible to write down deformations of Einstein. So here you have Einstein-Hilbert action, and I'm talking about full nonlinear level here. Here's a metric J, and here you have some matter fields which live on the same manifold as a metric, of course, MJ. Okay? And what Hainaut concluded is that this is the only action you can write down. So it's kind of a trivial action. There's no coupling between different worlds. Yeah, okay. However you want to think about it. It's very cool in how many ways you can think about that. But then came Damour and also Akani Hamed together with Georgi and Schwarz and said, no, it's possible. If I only allow for this reduced gauge symmetry, I can write down a deformation here, which contains only the different metrics. And then the question is, how can this deformation look like?
So these M1, M2 manifolds, are they diffeomorphic among themselves?
So that's, I will come to that question. Okay, the next slide.
Well, I'm just not sure how to define a diagonal that we put in one.
Precisely. So you have to think about when this really works. Yeah, so I'll come to that.
Why are we talking about different manifolds? I mean, these are different fields on the same manifold.
No. There are different possibilities you can think about that. So first of all, you can take one manifold and can make many copies of that manifold. That's precisely what we will do actually to evade that problem he mentioned. And it's probably what you are targeting at, right? So we will take one manifold and make different copies of that, and that will be a reformulation of cosmological perturbation theory, okay, in that context. So, okay, let's say, to make it, because I'm running out of time a little bit, let's say all these manifolds are diffeomorphic to each other for now. Then the leading coupling you can write down, the leading coupling term, has really kind of the appearance of a mask term. So you have two fields H that are coupled by a mass matrix, that if that is the leading infrared deformation is only polynomial, in the metric G, same metric that is used to define the geometry on this manifold. So we are basically putting back everything to the manifold we are sitting on. And then it's possible to define a field that's not a linearization, which consists of the metric that lived here and the pullback of the metric that lived here. Okay, so we can do that. So we have not linearized, okay, and then this is a legitimate term and we can study its consequences.
So the pullback is fixed once and for all?
What do you mean with once and for all?
I mean, this object y.
No, it's not. No, I mean it's not fixed in the sense if you change coordinates on the manifolds, you also change the pullback. It's coordinate dependent. But that's not a. I don't know what happened here.
Just click
OK. Good. So let me. Says had a bad box, but it doesn't look bad. I said, well, okay. So the old ideas these people had were the following. They were motivated by the following. Is it possible to make gravity, to give gravity a finite width in our world? So we can discuss that purely in 4 dimensions if you wish. But you can also have a setup, and that's coming back to those 2 questions, where we live on a brane embedded in a higher dimensional pipeline. Still this construction works, okay? In the first case, the linearization of that model gives rise to Fierz-Pauli theory of gravity. So Fierz-Pauli massive theory of gravity. Now the problem these people were asking, coming much more from phenomenological side, was, look, if I take just a Kaluza-Klein reduction, it's actually not a very good idea to truncate it everywhere. So I cannot come up with an effective theory of massive gravity without including all those terms. Okay? So that was not good. But then brane worlds came up. And whether you are a fan or not of brane worlds, it's not my point of view if they are good or not. I'm just showing the potential those models have here. Then you can come up with a setup, and this spectrum now is dictated by the geometry, where you have few massive resonances here, okay, and then you have a gap, okay, and then you can come up with a consistent truncation that gives you effectively massive 4-dimensional gravity. And that's also possible in other models like DGP or yeah, I mean basically brane-induced gravity models. Spectrum can always look like that. Okay, so now to the quality management, and that's probably where I get contact back again to you guys. So, okay, we have to use our field theory understanding to make sense of that. And here comes what is severely constraining these theories, okay? And that's the following. So okay, so let's extract the relevant degree of freedom. Now I have done a linearization, okay? Not a bad thing, I think. You think not, but let's do it, okay? And what I can do is I can split my gauge field into a transverse part, okay? And in something that's given as space-time gradients acting on a vector. And that vector I would like to interpret as a Goldstone vector, okay? Now, the nice thing about this vector is, because it has a helicity 0 contribution, I can always come up with this decomposition. I can split it up in a transverse part and a longitudinal part. And from many years of studies of these types of models in a different kind of environment, so people were doing a lot of brane stuff here, it became very clear that the problematic degree of freedom in this theory is helicity 0. But that's good, because that tells you don't have to solve full Einstein plus the deformation in order to address the issue. You can just focus on that degree of freedom because there's a famous theorem, the Goldstone equivalence theorem, that tells you if you go to high energies, and that's where we impose our quality management, because then curvature becomes less and less important, then the scattering of longitudinal degrees of freedom is basically given by the scattering of this helicity 0 part. And that's a powerful theorem. Why is it powerful? You can immediately see how it makes your life easier. Why? Because think about linearization over Minkowski. There, this guy receives no kinetic energy from the kinetic operator of the gravitons, because it basically looks like a gauge. Okay? So the only way this guy can receive kinetic energy is via the mass term. And the mass term is precisely what we would like to understand. Okay, now follow his example. Let's take a copy of two Friedmann manifolds and consider one as perfect a Friedmann universe and the other as a perturbed one. Okay? Now, the most relevant IR deformation of standard Einstein theory on that manifold is given by this coupling. Okay? So I have just considered now our longitudinal degree of freedom. So this is the way it looks like.
What's dot?
Dot is the time derivative with respect to the time we have chosen. So here I'm working in labs equals 1. So, and precisely, that's very important actually. What dot was important reminder for me. It's of course the question whether this is a healthy theory or not is dictated by the sign of the coefficient in front of phi dot. Okay, because that dictates whether I have negative norm states or not in that theory. Okay? Now, a remarkable thing happens. On Friedmann manifolds, this is a highly non-trivial question. Why? Look, you have a combination of h dot plus h squared. Now let's take radiation or matter-dominated universe. Then the sum of those two guys become negative, and the coefficient becomes positive. Okay? But now look, if I'm in a de Sitter universe, h dot equals 0, and I have a parametric dependence relation to fulfill between h and m in order to make that theory a viable theory. But in Friedmann it's much more difficult because it's not a parametric relation, it's a dynamical relation. Okay? And we'll see what the implications are. Do I have 5 minutes or? Thanks very much. So here, let's write down the Hamiltonian, and we see that the coefficient of A plays, of course, the important role, but there's also a stability bound coming in, which tells you that this theory can only be stable if A dot B is negative. Otherwise, the Hamiltonian becomes unbound from below. Now, quantum stability dictates that we only have positive norm states, okay, for that field. And this, again, gives a constraint on the sign of A and telling us, actually, that A has to be positive. Now, since A has to be positive, we only consider this requirement. So if that requirement is fulfilled, okay, then the perturbation does not destabilize Friedmann. Yeah, so there's no destabilization in the sense of that we lose control over perturbation theory. Combining this with a unitarity requirement, so that we only have positive norm states, gives us this beautiful condition. Now this condition is beautiful because it's a direct generalization of the Higuchi bound. So Higuchi found, so for Higuchi bound, you have to set all dots over H to 0. And what you then find is that the theory is only consistent for m larger than a cosmological constant. That's very remarkable. You have a theory that's consistent for m equals 0 and m larger than number, but not smaller. Okay? So there's this very famous bound on a massive gauge field on de Sitter. Now in Friedmann that becomes much more complicated because you cannot have just a parametric bound because H itself is running with time. However, the first consistency check we pass. So we can reproduce Higuchi's result, but we have a much richer phenomenology because now we have really not restricted us to the unique, de Sitter is unique in a way we all know, but we really have generalized to Friedmann spacetimes. And actually, this conclusion, and since I don't have time, I just will make the statement, this conclusion is independent of the matter you put on the Friedmann manifold. So that's also very important. Okay? Because you can ask, look, if I add a certain amount of energy momentum tensor on that manifold, will that change the result? And the answer is no. It's very funny. So the conclusion then that is matter independent is that a unitarity bound is robust against the matter impact, but most important actually, and that will come now. So I showed you many pictures of famous guys. This is my diploma student. Please remember him if he's looking for a job. Well, he first will do his PhD with Julius and me, and then he will be on the job market. He's a great guy. So he did everything that was not good. So now, now what is the most important result? The most important result is, first of all, there's a window of opportunity. But second of all, the stability bound was stronger than the unitarity bound. That means, before you hit the unitarity wall, which would definitely invalidate the model, you hit the bound for consistent perturbation theory. So you have to find nonlinear completion. In other words, the importance of the unitarity bound is nullified. And that's what people were not aware of. They always discuss these ghost issues, yeah, even on flat space, but and here we had a non-trivial space-time. But the point is here the theory is self-protecting. You first hit the bound that tells you, look, you cannot any longer work just in linear perturbation theory. You have to find a nonlinear completion before you go on. And then you would hit the unitarity bound. But the moment you hit the first bound, you have to stop and find the and consider the nonlinear completion of that theory. So in other words, these models are self-protecting and are clean. So that was the important message. Thank you very much for your attention.
I remember that Rubakov found some difficulties in frequent space and in superluminal propagation of gravitons. Is that related to this consistency condition?
No, so here I have not checked for causality and these things, but the point is, if I remember correctly, Rubakov was working with a mass term that was not Lorentz invariant.
That's right.
And that's a big, big difference. From my point of view, in this construction, it's impossible to get such a mass term. So I don't know how to justify such a mass term. And I think that's a defect of having a mass term that was not Lorentz invariant.
I mean, it's not terribly surprising that you get such things if you break Lorentz.
Precisely, precisely. So I never understood why people consider these non-Lorentz invariant mass terms.
Yeah.
Because look, I mean, effective field theory is not telling you should give up about Lorentz invariant.
Because it doesn't have ghosts.
Yeah, but
you avoid the ghost problem in this fashion.
yeah, but from my point of view, I understand that. So the way Rubakov put it was a competition between Lorentz symmetry and unitarity.
Yes.
And I think there is no such competition. Both things have to be fulfilled from my point of view.
And you're claiming you can do that?
Yeah.
Okay.
Yeah. So we did actually the full cosmological perturbation theory. So I just presented this Goldstone picture to you because this is something one can, I mean, it's just short formulas. But we have done the full solution. And the question is whether it's dequalitative or not. That's a different question.
So you still imagine two solutions, one ultraviolet and one infrared. You just showed us that there are ways to get the infrared one.
Yeah. So there's, actually that's very good.
I like very much your introduction and the framework, but I still think that this understanding that you and others, Andy Cohen, for example, over there, my professor for many years ago, this idea of the ultraviolet and infrared relevance,
Yeah.
the cosmological constant issue, to me remains, however, something that should provide motivation for the study of models where a single thing does both. So if you have a model that works and explains both the ultraviolet and infrared features of this problem, that's a compelling feature. I agree with you that the models we do have that do that, they mess up all the rest so badly that I'm not pushing for them.
No,
but I would say that your opening remarks, which I share, should be seen as encouragement for any approach that creates the connection between the two. So far, we don't have any believable approach, but we start to have something that does it.
I like your comment very much, but I just want to say, I mean, I think most of the time I also tend to think along those lines, but there's a different possibility, right? Because, see, what we learned over the years is, many times if we think only about ultraviolet modifications, about opening up degrees of freedom in the ultraviolet, in gravity, we thought that's it, and the quality management was not to touch the IR. So the IR was considered sacred. And that's a liable possibility. I mean, you can come up with ultraviolet modifications basically have no impact at all in the infrared. I think the nice point of that framework, I mean, Hainaut and Kogan and others and Schwartz came up, Kanye and Matt and these guys, the nice point of this framework is actually to say, look, I mean, you don't have to be scared changing something in the ultraviolet, which has also an impact in the infrared. The question is, what is the impact in the infrared? So you should not put that in the flash can right away just because you change the infrared storm. Markus, you're so silent, I cannot believe. Everything was great. So when I was here as a postdoc or as an assistant rep, actually, so Markus was always attacking me. And very good, actually, in the seminars. That's why I was expecting more resistance.
So we haven't had coffee, so.
Oh, yeah, sorry, yeah, okay.
So are there more questions? No, well then let's thank Stefan again. And
Achso, das ist jetzt eine neue Idee, wir haben das eine spezielle Anwendung davon, also wirklich zu fragen, die Geometrie Shadow ist. Und der Grund ist, wenn man sich jetzt so eine Landscape vorstellt, und dann sagt man normalerweise, kann ich mir kondensieren. Und solche Kerne ist es zwar möglich. Und da war halt die Frage, wenn es mal über das geht, dann könnten die über das Pullback und Shadow auf uns werfen und so aber das haben wir natürlich nicht aus, jetzt nur eine Idee, die da gerade rumspielt. Generator.